CPU scheduling is a crucial function of an operating system. Think of it as a queue in a restaurant, with the chef acting as the CPU. It determines how processes are assigned CPU time. This scheduling occurs during key events in the process's life cycle, such as switching from running to waiting, from running to ready, from waiting to ready, and termination. These transitions ensure efficient use of the CPU, preventing possible bottlenecks. For us to better understand what CPU scheduling is, we are going to look into its key concepts. First things first, the CPU burst time. This is the time that the process spends executing. Second is the I/O burst time, or the time that the process waits for I/O operations to complete. And last one being the final CPU burst time, aka the last segment of CPU time before a process terminates. Along with this, there are also several terms that are essential for understanding CPU scheduling, some of which are context switching, which saves the state of a process then loading another, preemptive and non-preemptive scheduling, which are techniques in scheduling that respectively allow and do not allow interrupting of processes. Throughput is the number of processes completed per time unit, arrival time when the process enters the queue, completion time, the time it took the process to finish, turnaround time, time taken from the submission of a process to its completion, waiting time, time the process spends in the ready queue, and response time, the time a process took the moment it arrived until it first responded. All of these are handled by the CPU scheduler and dispatcher, serving as vital parts of our operating systems since it is the one that manages the execution of processes. The scheduler decides what process should receive CPU time, then the dispatcher carries this out while also ensuring smooth transitions. In addition to this, schedulers have three types which are as follows. Long-term schedulers decide which process enters the system, short-term is for choosing which process is next, and medium-term for swapping processes. This brings us to the goals of CPU scheduling, which is to maximize CPU utilization, to increase throughput, to reduce waiting, turnaround, and response time, and to ensure fair and efficient process execution. Now, let's look at the key scheduling algorithms. These are systematic approaches to ensure efficient CPU time allocation. First come first serve, or FCFS, is the simplest of the algorithms, which executes processes based on their arrival time. However, this approach might lead to processes waiting for a long time before being executed. For example, we are going to look at this Gantt chart. FCFS is a non-preemptive technique in scheduling. The condition for the first come is the arrival time of a process, like in this example. If we take a closer look into the time completion chart, we can see that the processes are executed sequentially according to its arrival time, which gives us the completion time for each processes. For instance, it's burst time plus the burst time of all processes before it. Shortest job first, or SJF, chooses which process has the shortest burst time, but still risks starvation. SJF is also a non-preemptive scheduling, but instead of using arrival time like FCFS, the condition is which has the lowest burst time in the queue.
For our example, notice that the first process executed is P4 despite having a larger burst time than the others. This is because the schedulers did not leave gaps and the only thing in the queue at the time was P4. And because SJF is non-preemptive, P4 cannot be interrupted. After P4's execution, the queue has already been occupied by the rest of the processes, in which the scheduler can now compare burst times.
Shortest remaining time first is the preemptive version of SJF, which resolves starvation but risks higher overhead. In this algorithm, the system actively checks which process in the queue has the lowest burst time, including the current one. In this example, we can notice that P1 was executed first because it is the only one in the queue, but when P2 arrived with a shorter burst time than P1's remaining burst time, the system interrupted it for P2. The same thing happens as processes pile up in the ready queue. Round robin is the algorithm that uses a time quantum wherein it assigns a fixed time slice to processes. Our algorithm is preemptive and it uses a time quantum to give a time slice to processes. In this example, we can see how the time quantum works when the processes are interrupted evenly. This works by having the processor execute each processes bit by bit. When a process is interrupted, it moves in the back of the current queue and will be assigned a time quantum again later on. We also included in this example a ready queue, so we can visualize the interrupting of processes better as it moves back to the queue. Priority scheduling, which executes processes based on priority, which is good for critical tasks but still risks starvation. Priority scheduling's condition for the execution lies in an assigned priority number, with the low-end numbers being executed first. For instance, priority 1 is the highest priority. In this example, P1 is executed first because there isn't any process in the queue at its time of arrival, but the moment it finishes, the scheduler can now compare priorities, in which P2 was selected for having the priority 1, and then P3, then P4, and P5 as last. Last one is the preemptive priority scheduling, simply the preemptive version of the fifth algorithm, allowing for faster task completion but increased complexity. For our last example, there is the preemptive version of the last chart. P1 was still the first to execute, but the system interrupted it the moment P2 with a higher priority equals 1 arrived. And because P1 has priority 3, it was executed again after P3, which only has priority 2. To clarify things, when a process is interrupted, it returns back to the ready queue. This in turn contributes to the wait time of processes. And that wraps up everything about CPU scheduling algorithms. It ensures efficient and fair process execution, while also maximizing system performance.